This talk will explain our method for training pixel-wise photometric stereo networks. The photometric stereo method aims to recover the surface normal orientation map of an object from multiple images taken from the same point of view with varied illumination. Our work uses a CNN to solve this problem and achieves state-of-the-art results on real data using a synthetic data generation procedure. The related work for this problem is of broadly two main categories. Firstly, people have tackled it using direct optimization strategies. This amounts to inverting an image irradiance equation, which specifies that the intensity at each pixel is a function of the respective surface normal, light direction, material, as well as other variables. The main limitation of this approach is that the assumed reflectance model has to be simplified in order for the optimization to be tractable. This in practice means that global illumination effects such as cast shadows and self-reflections are mostly ignored, leading to systematic errors in regions where these are significant. The second category is using deep learning methods to learn the image to normal mapping. The advantage of deep learning is the ability to approximate highly complicated mappings as well as being robust to real data noise. The main challenge for deep learning is the very limited availability of real data, making training on synthetic data a necessity. However, physics-based synthetic rendering is slow, and a large number of images need to be rendered to sample the possible light normal material configurations. This limitation can be circumvented using multi-material rendering, such as this on Quijada's work, which sacrifice realism and widen the synthetic to real gap. To overcome this limitation, we directly extend Quijada's work and replace his data generation procedure. We completely avoid object rendering and we sample all the relevant parameters independently for each sample, approximating the global illumination effects. As a high-level summary, at test time, images are converted to observation maps, which are fed with CNN or reversed onwards. To train this network, we generate synthetic observation maps and approximate the global illumination effects observation map domain. Our procedure is very fast and generates data at real time during training, which results to state-of-the-art performance. I will now elaborate on several steps of our method. The first step is the image to observation map conversion. Following Quijada's work, for each pixel, all the different observations are mapped to a 32 by 32 image with the mapping coordinates being the respective light direction. The original work was using normalized gray values, however, we saw that including the raw RGB map as additional channels improves the performance. Now elaborate on the training data generation, which is our main contribution. For each training data point, we independently sample a surface normal, a set of lights, as well as material. More specifically, the assumed material either follows the Disney BRDF or is contained in the MERL database. Using this material, a set of reflectance components can be generated with either the Disney nonlinear equation or performing table lookup for the appropriate MERL material. Sample observation map is shown in the middle, both as RGB and normalized gray. We know that if our data generation process was to stop here, the training data would not include any global illumination effects. The result of this ablation of the Diels and Buddha is shown on the right, where it's observed that there is high error in most object regions, especially close to concavities. To overcome this limitation, we proceed to approximate the global illumination effects on the observation map domain. We start with cast shadows, which are caused when a part of the surface is blocking the light, thus turning the direct reflectance compute of the previous step to zero. To approximate this effect, we sample a variable height circular wall around the map and compute its shadow. This heuristic generates piecewise continuous shadows, mostly around the edge of the map, which is consistent with real data. We know that, as it will describe shortly, including more effects such as self-reflections, results to pixel intensity which will be non-zero for shaded light sources. Including the shadow modeling effect in the ablation of the data generation process significantly improves the error in most regions of the Diels and Buddha. The next step involves approximating ambient light and self-reflections. We approximate ambient light with a small additive constant, as being the de facto way in the literature. Self-reflections are more complicated and they occur when parts of the surface access auxiliary light sources. To estimate the computationally efficient approximation, we sample up to 5 points in this example A and B and compute a single light bounce from these points. Note that in the case of directional lights away from the surface, the self-reflecting points A and B are constrained to be part of the previously computed shadow. This is true as any ray extending from B outwards either intersects the surface or another point A or extends to infinity and intersect and so can receive light from a distant light source. For each of these self-reflection points, surface normal and albedo are independently sampled, but the material is assumed to be the same. We note again that including these effects on the training data significantly improves the ablation performance. Do look at our paper for additional model effects. We evaluate on the Diels and real dataset of 10 objects of varied materials and geometry, as well as other synthetic ones. Some quantitative comparison with CNSPS is shown here, where improvement is observed in most object regions. We also emphasize that we outperform other competitors and achieve the overall best performance. Finally, we know that our work can be extended to work in the near field, as we showed in last year's BMVC. In addition to that, we have a full near-field dataset available online.